Welcome everyone. Today we have a talk by Carlo Heissenberg, and he's going to speak about the eikonal exponentiation in gravity, radiation, and tidal effects. So please, you can start.
Thanks, Mitya, and thanks for the introduction, for the opportunity to present this talk, which is based on some recent work done in collaboration with Paolo Di Vecchia, Adolfo Russo, and Gabriele Veneziano, and also on a recent paper more about these tidal effects I'm going to touch upon in the end. So the idea in this talk is to illustrate some recent techniques that allow us to extract information from scattering amplitudes and to apply this information to calculate gravitational observables associated to binary systems and the emission of gravitational waves by these types of system. And I'm going to use in particular a technique which is called eikonal exponentiation, which allows us essentially to extract the classical limit from the amplitudes in a systematic way. So the idea is to start maybe with more of an introductory part and to motivate the discussion a bit better, and to also illustrate this technique, this eikonal exponentiation in a setup where it is fairly well understood and well established, which is the classical limit of an elastic 2-to-2 amplitude, which, I mean, probably we would essentially occupy the first half of the talk. And then towards the end, I will instead discuss some more recent developments which have to do with the inclusion not only of 2-to-2 processes, but also 2-to-2 plus graviton processes, so processes in which we take into account more precisely the emission of gravitons and gravitational waves in the classical limit, and this will essentially lead us to promote this eikonal phase to an operator. And then I will discuss essentially how one can use this operator to calculate a larger class of observables compared to the elastic case, and also to include tidal deformations. So let me begin very broadly by introducing the main motivation for this kind of calculations, and which has, of course, to do with the very nice measurements done by LIGO, Virgo, and associated experiments of gravitational wave signals emitted by coalescing compact objects, pairs of coalescing compact objects called binary merger events. And this is a very nice cartoon that essentially gives the idea of the nice progress that these experiments have brought about. And in particular, as we are probably familiar, since this has been also a topic covered in many essentially news or popularization contents. So essentially these type of systems are essentially the evolution of these types of systems can be divided roughly into two parts. There is a first part in which the two objects that orbit around each other stay very far apart and still interact weakly. This is the so-called inspiral phase. And then eventually these two objects get closer to each other and eventually undergo the merger proper, which of course involves very strong gravitational interactions and requires, in order to solve the equations of motion and the Einstein equations, to resort to numerical calculations. Now, this early phase in which gravitational interactions are weak luckily lends itself instead to analytic approximation methods. Essentially, let me highlight three of these types of methods. For perhaps the most time-honored and also the most appropriate ones as far as bound systems are concerned is the so-called post-Newtonian approximation, which as a slogan can be thought of as an expansion for small g, g being the Newton constant, and large c, or small velocities. Or more precisely, this is an expansion in two dimensionless parameters. One is essentially the ratio between the typical sizes of these objects and their distance. So this would be essentially the Schwarzschild radius, or half the Schwarzschild radius divided by the distance. And the fact that this parameter is small just means what I was saying in words, namely that the two objects stay very far apart compared to the typical sizes. So indeed, gravitational interactions are weak, and also for small velocities compared to the velocity of light. So v over c squared small. So this is essentially also a non-relativistic regime. And in fact, for bound systems in which these orbits are essentially quasi-circular or of elliptic type, indeed, these two parameters are always the same of the same order by the virial theorem. Another type of expansion one can form is instead the so-called Post-Minkowskian expansion, which is essentially only an expansion in powers of g, in the sense that one assumes that this parameter be small, so objects should still remain far apart compared to their sizes, but in general need not have small velocities compared to the velocity of light. Now, this other regime can be either thought of as a resummation of the post-Newtonian limit to all orders in the velocity, or as a sort of more ambitious approximation in which one does not necessarily focus on bound orbits, quasi-elliptic orbits, but one can also look at scatterings, in which, for instance, the virial theorem does not hold in this form. And in fact, this will be the one that most naturally correlates to amplitudes. And this will be the approximation I'm going to focus on in this talk. And okay, just for completeness, let me also mention this other self-force expansion, which I will not touch upon, which is instead an expansion in which one assumes that one of the two objects is much lighter than the other one, so that to first approximation, the system can be considered as a probe particle moving in the background of the metric generated by the more massive particle. And there is it's actually a very powerful technique that allows you to, especially when compared to the other ones, to determine a lot of coefficients in the overlapping regions. So let me essentially state the idea that I'm going to try to develop in this first part of the talk, which is the following. Why don't we extract this Post-Minkowskian limit, this Post-Minkowskian expansion for the gravitational dynamics from scattering amplitudes? Now, of course, at first, this may seem a bit roundabout because, after all, I mean, scattering amplitudes encode much more information than what we want in order to only discuss classical systems. They also contain quantum corrections, of course. But there are essentially two intuitive ideas why this could sound like a successful strategy, potentially. Well, the first one is that amplitudes are already organized in a sort of G expansion, right? Which is very, very akin to the Post-Minkowskian expansion I was mentioning in the previous slide. So this is just the usual weak coupling expansion of quantum field theory, which labels each order in perturbation theory by a power of the coupling. And a second reason is that, of course, amplitudes are also informed by Lorentz invariance and therefore naturally capture processes with generic velocities. So indeed, this seems very natural to connect with the Post-Minkowskian expansion, where we do not assume that velocities are small compared to the velocity of light, so we stay Lorentz invariant. Now, as a disclaimer, as I will develop in the next few slides, this connection is indeed possible and convenient, also because now we have a lot of techniques that allow us to construct amplitudes in systematic ways, like gauge gravity, gauge squared equals gravity, and so-called double copy, and also techniques that allow us to perform integrals in a very convenient manner, like IBP reductions and so on. So let's say technique borrowed from collider physics. But okay, as a point that may be worth maybe discussing later on, one should bear in mind that even if one studies scattering events, there are some informations, in fact, several information, and one can in fact carry over also to the bound trajectories that are in fact more appropriate for calculations that are important for Virgo and LIGO. For instance, if one manages to probe the effective potential between the two objects, so determine an effective Hamiltonian, even if this has been determined in the scattering case, then one can also export it to the bound case. One just needs to change the boundary conditions, but the Hamiltonian essentially stays the same. And then there are other techniques that essentially can be thought of as analytic continuations from certain observables in the scattering case to corresponding observables in the bound case. Essentially, one performs an analytic continuation from energy bigger than zero to energies smaller than zero. And for instance, an example of this is the fact that the deflection angle for the scattering event that we'll be discussing in the first part of the talk has an analytic continuation which translates in the precession angle for the quasi-elliptic orbit. So maybe let me try to make the discussion a bit more precise. I will be focusing on the scattering in this post-Minkowskian regime of two spinless objects, which for the first part of the talk will be considered just some point-like objects, and effectively are modeled by scalar fields in the amplitude side of the story. This is sort of a cartoon of their scattering as seen as in the center of mass frame. And let me try to be a bit more precise as to what I mean by saying that this system is a classical system and in this post-Minkowskian regime. So the first requirement is that the typical wavelength, quantum wavelength associated to these objects with mass m should be much smaller than their typical classical size. And so, for instance, the Compton wavelength here is of the order of h bar over the mass, and this should be much smaller than, say, the order of the Schwarzschild radii, GM. And in order for the post-Minkowskian regime to be valid, to be appropriate, we should also enforce that their distance, so which in this case is sized by the impact parameter B of Bj of the collision, should be in fact length scale much bigger than both their typical sizes and the quantum wavelength. So these two inequalities can be rephrased in this way. Gm over B much less than 1 is the familiar post-Minkowskian approximation. And then you see the other translates in the requirement that Gm squared is much bigger than h bar. So indeed, if you want, this means that in a sense, the effective angular momentum of the system is very big in units of h bar. So as familiar, like the classical limit obtains when classical charges are very big. But as you can see, this poses sort of a problem from the slogan I tried to advertise in the previous slide. Namely, as you can see, this is a non-perturbative limit from the if you want, quantum field theory side, because G is not small. In particular, when it appears in this combination, Gm squared is very big in natural units. And so one needs to do something in order to extract the appropriate classical limit from, say, a perturbative scattering amplitude that we are used to calculating. And there is a tool in order to perform this limit, which is the elastic eikonal exponentiation that then I will try to illustrate. By the way, feel free to interrupt and ask questions at any time, of course.
So I want to ask one thing.
Please.
So you said that B is much larger than the Schwarzschild radius, right?
Yeah.
But how it's compatible with like the system that you are going to describe, in which black holes like eventually collide?
Exactly. So that's why I was making this sort of disclaimer. So in this talk, I'm never going to talk about true coalescence processes of black holes. I will instead consider events which have a cartoon of this type, in which the two particles interact, but then eventually scatter off to infinity. So that's why I was saying I'm not considering bound orbits in which, as you say, eventually the things get closer and closer together and merge, like in realistic scattering, LIGO observed coalescence events. But rather, I'm going to talk about the different type of processes, which are these classical scatterings, really.
Yeah, but you still said that there is analytic continuation to that regime. Is it?
Yeah, there is an analytic continuation in which you manage to map some of the calculations you do in this setup to the very early in spiral phase, in which you basically assume that these orbits are, quasi-stationary elliptic orbits. So still you are in a regime in which the things are very far compared to the typical size. If you want, okay, I should have said it, but if you try to plug the actual numbers here for LIGO events in this early in spiral phase, replacing B with the typical separation, you see that this parameter is of order roughly 1/6, which means that it's reasonably small to do some perturbation theory, but it's not that small, so you cannot restrict to the leading order in Gm over B, and that's why people have to go subleading either in the PM or in the PN framework.
Mm-hmm. Yeah, okay, thank you.
Yeah, so if we really want to extract some information about this type of system from amplitudes, the first thing that comes to mind is to consider an amplitude of this form. Basically, we send in, here I'm considering this all outgoing convention, but essentially P1 and P2 are the incoming states. So we send in two particles with mass M1 and M2. We have some other two particles with the same masses in the outgoing states. And of course, this amplitude will encode some information about the dynamics of this process, right? And the question is how would we extract it? So as usual, the amplitude is a function of two Mandelstam, independent Mandelstam invariants, S and T. S essentially is a measure of the relative speed, or if you want, of the center of mass energy squared of the two objects. I will also use this parameter sigma, which is essentially the relative gamma factor or Lorentz factor. So it tends to 1 when the system is stationary and to infinity when the two objects move very fast. And instead, T is a measure of the transfer momentum in this amplitude, which I will call Q. Now, the first step that we have to do is that we have to introduce this impact parameter I was talking about. And essentially, this means that we have to translate the amplitude from momentum space to position space. So this involves a Fourier transform with respect to this transfer momentum. And okay, this Fourier transform is performed in the plane orthogonal to the incoming direction of the particles, right? Essentially, this is all the possible impact parameters are in this orthogonal plane. So, okay, this is just a rewriting of the amplitude in this other basis, if you want, in this position basis. And the convenience of this B space representation is that in this form, the amplitude exponentiates in this nice way. And this is what goes under the name of eikonal exponentiation. I will come back in a second as to what extent this has been proven, and this is just, and to what extent it's instead just a sort of well-educated guess. But let me first try to illustrate its features. So on this side of the equality, there is our standard perturbative amplitude that we can expand in 3 levels, plus 1 loop, plus 2 loops, etc., etc. And here instead this phase, which has this property that to leading order, it scales precisely like this large classical quantity here, gm squared over h bar. So if you want restoring h bar, you can think that this thing is divided by h bar. So basically, what we have done is that by resumming these contributions, we have reconstructed the appropriate rapidly oscillating behavior that the amplitude should indeed have, also, based on expectation from WKB and other similar techniques to calculate classical approximations of quantum mechanics. And then it receives corrections on this leading behavior of this order here. And these corrections are of order, are small in the sense that they are of this order here. So for instance, this delta 1 is suppressed with respect to delta 0 by 1 power of gm over b. And then delta 2, which would be the 2-loop contribution, is suppressed by a further power of gm over b compared to delta 1, and so on. So basically, this is the nice quantity that takes care of this singularity in the classical limit that the amplitude has, which is just, it's just a feature that appears because we have expanded in G a thing that actually is a rapidly oscillating thing. But on top of that, it only receives nice corrections that are perfectly under control in the post-Minkowskian regime. I will give an example in the next slide that hopefully makes this technique a bit clearer. But let me just explain what we do with it once we have extracted this rapidly oscillating phase. Well, we can calculate one observable in particular about the classical process. And to do this, we can simply go back from this exponentiated form in B space. We can go back to momentum space by performing the inverse Fourier transform. And as you can see, since this phase here is rapidly oscillating, as I was saying, this integral is dominated by the stationary phase approximation, which determines Q mu, which is now the classical saddle point, right? It's just the derivative of the real part of this delta. And indeed, each of these orders in the expansions of delta determines the PM approximation of Q. So for instance, delta 0 will determine Q1 PM. So the first post-Minkowskian contribution to the so-called impulse, so this deflection vector here. and so on. The 2 p.m. will be determined by delta 1, and the 3 p.m. by delta 2. So let me try to illustrate this in the simplest possible case, which is the leading order. So of course, to leading order in the perturbative amplitude side, we just have this one graviton exchange, which takes this form. And in B space, so we can perform the Fourier transform of this amplitude here, takes this other expression here. Now let me maybe comment on the fact that here there is this gamma of minus epsilon. Epsilon is the dimensional regularization parameter, and we only need to introduce it because in 4 dimensions, gravitational interactions are long range, and this is just the familiar Coulomb logarithm that appears once you expand out this factor here, right? For small epsilon, you will get a B-independent pole, and then logarithm of B, which is a signal of this Coulombic-like behavior of gravity. But more importantly, now let us use this B space amplitude in order to perform the calculation I was sketching in general in the previous slide. So we should match this amplitude to this eikonal exponentiated form, and to leading order, as you can see by formally re-expanding delta 0 for small g, you see that this simply determines 2 delta 0 to be equal to this B space amplitude. In fact, as promised, now here I haven't reinstated h bar, but as you can see, this quantity scales precisely like gm squared over h bar. So indeed, this is a very large quantity. By the way, if you plug in the numbers of typical black holes that LIGO and Virgo observe, this ratio gm squared over h bar is of order 10 to the 75. So indeed, this is a very big object and is not a small perturbation in the usual sense, right? It's not small compared to 1. And that's the reason why we have to do this resummation. And now, okay, we can just determine the leading order deflection vector or impulse by taking the derivative of this. And this is the expression, which if you turn it into the angle, which is dimensionless, indeed, as you can see, scales like gm over b, or g the energy over b. So it's proportional to the leading pm, to the small pm parameter. Now, intuitively, as I try to highlight this picture, this exponentiation takes into account the fact that classical gravitational interactions are mediated by the exchange of a large number of gravitons, right? So not just one graviton, which, you know, by duality in the Fourier transform has a momentum transfer q of order h bar over b, right? Which is, of course, quantum. But by resumming the exchange of effectively infinitely many ladder exchanges of gravitons, like in this picture, eventually leads to a classically finite deflection given by this expression here, in which no h bar appears, even if you reinstated h bar different from 1, and you wouldn't find any h bar here. This is already of the dimension of the impulse. Now, as far as proofs are concerned, one could complain that this seems to be just a guess, right? Now, this exponentiation of delta 0 has been actually proven, in particular for the case of massive particle scattering in these 2 nice papers. Here is a review which also extended a little bit to the next order. And essentially, this is a precise statement in the sense that now the statement is that if you expand this thing, you will have the exponential series, and that at any order, you will have something of the type 2i delta 0 to the n divided by n factorial. And the statement is that if you look at the n loop order, you should find, sorry, n minus 1 loop order, I guess, you should find that the most singular term in 1 over h bar, or more precisely in gm squared over h bar, is precisely given by this expression. If it's not, it means that you have made a mistake in your calculation, because okay, this is a proof that people showed. The distribution for subleading eikonals is a bit less solid, let's say, but I mean, guided by this intuition that the classical limit should exist and should lead to this high rapidly oscillating phase, it seems to be essentially a flexible tool that works in all examples that have been considered so far.
Sorry, I'm a bit confused. Why is this just not a notation? You just take log of the right-hand side and denote it delta.
Yeah, no, okay, let me try to explain it a bit better. So suppose that it becomes slightly clearer if one considers the one loop case, which I didn't consider, but let me try to sketch it in words. So suppose that I go to one loop now. I don't just consider this amplitude here, but also diagrams of this kind, for instance, and all the one loop ones that you have. You just compute them, and you Fourier transform them to B space, right? Now, it could well happen that if you expand for this large B regime that we are interested in, you find, a power series or some terms. Now, this is a sharp prediction because it means that the term proportional in this case to this quantity squared must be already known from the tree level, which I've calculated in this slide. It's a prediction about this term that goes like, in particular, okay, b squared to the 2 epsilon instead of the 1 epsilon like here, right? And the coefficient must be precisely this function squared. So if that's not true, it means that this formula is wrong in the sense, right? If you want, the assumption is in this scaling that I was saying here. Of course, if you would allow any scaling with h bar, both positive and negative here, then, as you said, it's just a rewriting. But the claim is that this quantity scales precisely like 1 over h bar in front, and that's it. There is no, 1 over h bar squared, for instance.
Yes.
Otherwise, as you said, it would be an empty statement. And as you see, this is crucial because when you take this derivative, effectively, you are removing just 1 power of h bar, by dimensional analysis. And so if you had 1 over h bar squared here, you would get a quantity that does not behave well here. This is a classical observable, so you shouldn't have any h bar if you want. So it's crucial that this is the scaling for the eikonal because this determines finite classical quantities. I mean, well-defined classical quantity.
Okay.
Thanks for the question. Any other clear points?
Maybe you can remind, so Q is the momentum transfer, and Y by Fourier transform it goes to the impact parameter.
Yeah, okay, you can, I mean, intuitively that's rather clear, right? Because, of course, you will have a large momentum transfer when particles get closer together in the impact parameter space, right? They will interact more and therefore deflect more. You can see this more mathematically by considering some wave packets, if you want them to have well-defined position instead of well-defined momentum, you will have to do a Fourier transform. And essentially, if you take the wave packet, act on it with the S matrix, and work your way until the end, you will find that this, after some changes of variable, precisely this Fourier transform appears. There is a nice discussion of this point in a recent paper by Donald O'Connell and collaborators that I think I cite a bit further on. And, anyway, yeah, I can direct you to that paper if you want to see more, details about this step.
Okay, thank you.
Okay, let me maybe, before going to the, let's say, new developments part, just flash the exact same, the result for the exact same quantity, so the eikonal, calculated more or less in the same spirit, but of course with more technical steps in between because one has to do some loop calculations. Let me just give you the expression for the 3 p.m. eikonal. So of course there is also 2 p.m. eikonal, which is interesting, but let me just jump to something that we did recently, and just before moving to the more recent developments I wanted to talk about in the second half of this presentation. So this is the expression for the two loop, or if you want 3 p.m. As you can see, there is a power of g cube here, phase. And okay, the different color code means that some of them, in particular the first line, these green terms can be actually determined by looking at the probe limit I was mentioning, basically at the limit in which one of the two particles is much smaller, much less heavy than the other one. And the ones in red are instead been instead calculated by Swinburne and collaborators, and are so-called potential terms. Physically, essentially, they encode the fact that each of the two colliding objects feels the attraction to the other one via the effective gravitational potential. And then there are these blue terms that we determined that which are instead due to different types of effect, namely, it's the first order in the G expansion in which also dissipative effects enter this eikonal, and therefore the deflection angle, the impulse. And so these are sometimes dubbed the radiation reaction effects. So these are, in fact, as highlighted by Thibaut Damour, also in a very nice paper, these are due to the fact that the system loses some angular momentum, loses it due to the interaction with the gravitational field at 2 p.m., so at order g squared, and this back reacts on the trajectory at 3 p.m., and so leads to essentially a slight enhancement of the deflection angle, by taking the derivative of this with respect to b. Now, this is particularly important, the interplay between this essentially conservative type of effects and this dissipative type of effect is particularly important when one looks at the high energy limit of this angle. So in particular, in the limit of high energy, or when this parameter sigma, is just basically the gamma factor. I don't know why, but people started calling it sigma in this line of research. 1 over a square root of 1 minus v squared, if you want. So when this goes to infinity, one essentially would like to see whether or not the answer reduces to the answer that one gets for the scattering of some shock waves that move at the speed of light, right? Or if you want, it's a regime in which the energy is so big that the masses of these objects can be neglected. And indeed, the complete expression for the eikonal is smooth in this limit, but this is non-trivial, as you can see, because there are in particular these arc-Cosh functions which become logarithms of sigma at high energy, or for large sigma, and separately they would lead to some logarithmic enhancement of the result, which is not present in the known massless result by Amatrice, Ferroni, Veneziano, dating back to the 90s. And indeed, the logarithms cancel only in the sum. So if one also includes these blue terms, and moreover, the remaining coefficients precisely combine in order to reproduce the result obtained in the massless case. And moreover, this is also very nice because it's in some sense universal. It's a universal high energy limit that is common to all theories where the massless particle with the highest spin is the graviton, essentially because it's the one that couples with the highest number of powers of the energy. And in particular, we checked it's the same also in unequalate supergravity. Very good. So the situation with this elastic eikonal seems nice, and says we can obtain this deflection angle up to 3 p.m. and the deflection vector and deflection angle up to 3 p.m. and everything seems nice and consistent. But okay, let me try to highlight a couple of things that are instead not nice, and we would like to improve on in order to move to the next part. So in this setup, one essentially is saying that the final state of the collision, of course, this is a bit schematic, but I think it conveys the main idea that I want to emphasize here. Essentially, only differs by the in state by this quantity, which is this rapidly oscillating factor, right? E to the 2i delta. And there is a first problem, namely, if you now take the norm of this state, you see that due to the fact that this delta has also an imaginary part, which precisely starts at 2 loops. I had written it here. In fact, there is a nice story as to why it's proportional to the blue terms that also enter the angle, but let me not go in that direction. For our purposes now, it's important just to stress that there is an imaginary part in this eikonal, and it's also infrared divergent. So in fact, it blows up if you consider the case strictly of d equal to 4. So the not so nice thing is that if you want to consider this norm and you really set the dimension of the spacetime equal to 4, you see that this norm is 0. So it basically means that you consider the process in which the final state can never occur. And this is actually the manifestation of a well-known fact, namely that in 4 dimensions, any scattering must be actually accompanied by the emission of at least some gravitational radiation that we did not consider, right? Because we were just considering the 2-to-2 amplitude by construction. So this means that in order to obtain a more, consistent setup, we should include the information about some emission of gravitons. And okay, even for more practical purposes, this is needed also because this formalism that I discussed so far does not allow us to perform any calculation of gravitational observables associated to the gravitational field itself. For instance, what if we wanted to calculate the metric fluctuation that is sourced by the scattering event at some point very far away, which is in fact the wave form that, okay, in the coalescence case is observed by LIGO and Virgo, or if you wanted to calculate, say, the energy and angular momentum emitted via gravitational waves and check that these energy and angular momentum lost are indeed, of the gravitational waves correspond to exactly to the loss of the same quantities by the two-body system. So this formalism with the elastic eikonal does not allow us to answer these questions because it all involves 2-to-2 amplitudes, so we don't know what to do. So in order to answer these questions, I will now try to introduce a new ingredient and combine it with the previous one by considering this new setup, which goes under the name of eikonal operator, which of course builds on some proposal already present in the literature, but we have essentially been developing recently in order to perform these different types of calculations. So the new ingredient is going to be another amplitude. So not only we are going to use this 2-to-2 amplitude that I've been discussing so far, but also an amplitude in which we consider the collision of the two objects, their scattering, and the emission of, okay, to start with just one graviton. With this K, of course, this is not the actual topology. It's just meant to help us remember that the way in which we define these two variables Q1 and Q2 is such the way that they add up to 0 together with K, which is the graviton's momentum, say for momentum. And okay, another natural step is that we also have to take an impact parameter Fourier transform akin to the one we considered in the elastic case. The novelty is that in this case we have two, if you want, momentum transfers, not only Q as in the previous case, but this Q1 and Q2, right? And so we define this A tilde mu nu, which is this new fundamental object, if you want. And the idea is to combine it with the eikonal exponentiation by considering two main approximations. So the first one you see here is the first ingredient of this eikonal operator that we propose is to still, of course, include the fact that the two particles interact, and they interact by these ladder exchanges or generalized ladder exchanges of gravitons. You remember the picture I had at some point. So this capture this eikonal exponentiation of graviton exchanges. And here, instead, we consider as a first approximation the emission of coherent gravitational radiation. So A and A dagger are annihilation and creation operators for the graviton polarizations, and A tilde J is the projection of this A tilde mu nu that I introduced in the previous slide on the Jth polarization. Now, this is, in a sense, a proposal, so one has to test it. Of course, the most non-trivial test would come from considering a one-loop amplitude with the emission of gravitational radiation, right? But by considerations analogous to the ones we were discussing with Mitya a couple of minutes ago. So only looking at the next order, one sees if the ansatz for the exponentiation is actually the right one, right? In order to, one has to check these singular terms in H bar, but this is not known at the moment, so we have to do some other tests. Okay, the first test is that it should reduce to the previous exponentiation when we do consider only scatterings between elastic and two particle and two particle states, both in the initial and the final state. And indeed, this is the case. So if you project back this final state obtained using this eikonal exponentiation, you project it back on an initial state which only has the massive state. You see that in order to use the fact that the vacuum is annihilated by A, you have to separate this this exponent into these two pieces, and you have to use the Baker-Campbell-Hausdorff formula to perform the commutation relations. And in fact, one can show that precisely this new term that comes from the BCH formula precisely gives back the imaginary part of the eikonal and therefore reconstructs the complete eikonal. So in a sense, this is a proposal which is consistent with the previous one, in which, you know, if you consider 2-to-2 scattering, you get back the 2-to-2 eikonal. And okay, and then there is a nice feature that we included by construction, which solves the first problem that they advertised in the previous slide. So this quantity is manifestly Hermitian, and therefore this operator is manifestly unitary. So now the final state indeed has the same norm as the initial state. Okay, this is nice in theory, but I mean, can we also use it to calculate the observables that I was complaining about in the in the motivation slide for this second part? And so let's try to apply this new operator that we constructed to do some new calculations of observable quantities. So the first quantity we can calculate is indeed this metric fluctuation. So of course, if we take the expectation value of the graviton operator, if you want, the canonically quantized in-two field in the final state dictated by this eikonal operator, of course, you know, the A's will pull down the A daggers from the exponentials, etc., etc. And essentially what you find is that if you then take the asymptotic limit for this metric fluctuation, which of course is the only reliable region, of course, right? We do not expect the perturbative calculations to be valid near the colliding objects, but only very far away, say in a null direction. And one finds that in the limit that considering, as I said, a detector very far from the collision, from where the collision actually takes place, you find essentially that the waveform, this metric fluctuation, becomes proportional to this A tilde mu nu up to a Fourier transform in the frequency, if you want. But with a slight abuse of notation, we can essentially say that this A tilde mu nu is the gravitational waveform. And let me emphasize, okay, a technical but also important point is that this A tilde mu nu we consider will always satisfy this property that being exactly transverse to the graviton momentum, so to satisfy gauge invariance. This is going to be particularly important for applications in the next few slides. Okay, so that's very nice. So we managed to calculate the gravitational waveforms, and by the way, this was not the first time it was presented, this formula. I mean, in this way we see how it comes about from the eikonal operator, but in fact similar formulas have been derived also in previous papers. And let us use it to calculate some other quantities. For instance, what about the energy momentum that is radiated via gravitational waves? This has been also calculated in this other paper here, but essentially this shows how we can get it out from the eikonal operator. Well, one inserts the momentum operator for the gravitational field in the final state, so the same strategy as for the previous one. Let me call it bold symbol P. This is the expression. The fact that K mu contracted with A tilde gives 0 is nice because it allows us to, you know, rewrite the sum over polarizations in terms of this nice combination that is independent of any reference vector. And then there is a technique which allows us to do this integral explicitly using, as I briefly mentioned this type of techniques earlier, right? These IBP reductions and similar collider physics, let's say, inspired techniques that are very useful in order to perform these loop calculations. I don't want to go in details here because I essentially don't want to focus on that aspect, but in this paper here and others also, it has been noticed that these type of calculations can be, you see, these are calculations that involve products of Fourier transforms of 5-point amplitude. Well, it's actually much easier to recast them as a convolution of 5-point amplitudes in momentum space, which then eventually only Fourier transforms only at the end. And the usefulness is precisely that these type of integrals in momentum space, these convolutions in momentum space, one can treat using these, you know, IBP reductions, and this is the so-called technique that goes under the name of reverse unitarity, because essentially one sometimes uses, you know, unitarity to say that the imaginary part of something is given by an integral of this type. In this type of games, one uses this relation in the other sense. So one wants to calculate an integral of this type and knows the full expression without this cut, right? And one just need to take the imaginary part of the known result to get the value of this cut. Very nice. So this is a way to reproduce a result present in the literature. Let me discuss a slightly more complicated one, which is the angular momentum. Again, the strategy is very similar. You insert the angular momentum operator for the canonically quantized gravitational field. Let me, in particular, focus on this type of calculation, the types of contributions, that again I denote by bold symbol J, which are the ones really associated to dynamically propagating gravitational waves. There are also other contributions that, for the moment, I don't want to discuss. We also calculated them, but they're actually easier, so that maybe we can discuss them later if there is interest. But the calculation of these types of terms is again very similar to the one discussed here, and had been performed by different techniques also in this paper by Shen and collaborators. But here, we basically find a way to perform this calculation again in the same spirit as the one I discussed here. The slight complication in this case arises because of the presence of this derivative, right? That comes in if you want, from the orbital part of the angular momentum. There are these derivatives with respect to the momentum of the graviton, and this makes the rewriting, of the product of Fourier transforms as a convolution, which is then Fourier transformed at the very end, a bit harder. But if one works through it, eventually one finds an expression of this type. So the first line of this expression is essentially the naive one, in which you basically ignore the presence of the derivatives, perform the step anyway. You write it as a convolution, which is eventually Fourier transformed, and you still keep these things acting on the amplitude. But being careful, you see that instead you have to consider also another type of terms that essentially arise with an integration by part that cannot be thrown away. And this is an additional piece that you have to consider. Again, the technical usefulness of this step is that both of these integrals are trivial to calculate once you know these integrals for the two-loop case. And instead, maybe I should have emphasized it earlier. Of course, one could say, why don't you just do the integral at this level? Why do you need to go through all of this? The reason is that this A tilde has a slightly complicated form. It involves some Bessel functions, there is a parametric integral over a Bessel function. Then, taking the square and then integrating over the phase space of the graviton is not entirely trivial. Instead, in this case, these expressions in momentum space are just rational functions. So it's easier to calculate integrals of rational functions, which we have all these techniques and machinery for. And now let me discuss instead a new application of this formalism, which is the angular momentum that is lost by the system, right? In fact, we can perform the similar calculation for the momentum that is lost by a single particle. Again, the technique is very similar, and you find this result here, which obeys these relations. So I'm not spelling out exactly what this calligraphic E function is. It's just a complicated function of this parameter sigma. I have it in later slides, but it's not very illuminating. The main message I wanted to convey is that using these techniques, you can perform two calculations separately. On the one hand, calculate the radiated energy momentum of the gravitational field, and on the other hand, calculate the changes in energy momentum of the single particles. And you will see that these things precisely add up to zero, as they should by energy momentum conservation. So a new calculation that we did was to perform the same thing, but for the mechanical angular momentum. So again, we can go through the same type of discussion. We insert the angular momentum operator, say, for particle number 2, the final state, compare it with the one in the initial state, take the difference. Let me again focus on these bold-faced terms, which are the relevant ones for the radiative effects, for the losses due to the emission of gravitational waves. This is the expression in terms of this A tilde, the complicated function, the Bessel function, etc., etc. there is this nice set of steps that you can do in order to map it to a nicer integral, which involves momentum space convolutions, which we know how to calculate, and then eventually perform the Fourier transform at the very end. These are the expressions that we get. Again, the explicit formulas for F and calligraphic F and calligraphic E plus are given later on, but they're not very extremely illuminating. But maybe I will discuss them just to mention the space of functions that appear, which is also interesting to some extent. But again, the main point is that we perform these two calculations separately. This one is a new calculation, and we, by adding all of these terms together, you see that again they obey the balance law as expected. So in other words, the angular momentum that is carried away by gravitational waves does indeed correspond to an equal and opposite loss of angular momentum by the system. Now, here are the expressions that, as promised, are not very very transparent. Maybe just one thing that I wanted to mention is the fact that aside from these functions here of sigma, which are basically polynomials, okay, there are also some square roots, one could complain, but these are actually slight artifacts as to how people actually define the overall scaling. It's actually nicer to define it in this way, as you can see, where no square roots appear. But the important point I wanted to make is that you remember I mentioned at this point this business of analytic continuation. So basically, as I said, the sigma for the scattering dynamics is a parameter that goes from 1, in which the case in which the particles are sitting still with respect to each other, to infinity, which is the limit in which they move very fast. And okay, the analytic continuation of this result obtains by extending sigma to the interval from -1 to 1, which basically correspond to a bound system which has less energy than the sum of the two rest masses. Now, as you can see, this function is perfectly analytic, even if you continue it to sigma smaller than 1. Smaller than 1, provided that it's still bigger than -1, because otherwise, as you can see, you hit the branch cut of this logarithm. This function is slightly less clear, right? Because it seems to have a branch cut also at sigma equals to 1, plus 1, I mean. But this is actually cured by the presence of this arc-cosh. So you can see that this is actually an analytic function for sigma bigger than -1. And in particular, it's still analytic across sigma equal to 1, which is if you want, the dangerous point, in a sense, from going to the unbound case to the bound case. So essentially, what you have to do, you don't have to do anything. These expressions are also already valid for the case of bound trajectories, provided you reinterpret sigma in the way I was saying. Very nice. So let me just in the last few minutes, let me just mention how one goes about extending these calculations I illustrate in the second part, in part 2 of the talk, to the case of objects which are not point-like, but can also have some internal structure and are therefore some subject to tidal deformations. So essentially the main conceptual step one has to go through is that one has to modify this additional ingredient I was mentioning, which is this 2 to 3 amplitude, and okay, add terms that are due to the presence of additional operators. So on top of the minimally coupled scalar Lagrangian, there will be some additional terms in which powers of the Riemann, of certain combinations of the Riemann tensor appears. In particular, I've considered these so-called electric type or magnetic type, or also called sometimes mass type or current type tidal deformations. And okay, they are the leading ones. So that they appear as linear terms in the equations of motion. So let me skip the comment about the explicit form. Again, the procedure is the same. You consider the insertion of the energy momentum in the final state. You have to consider this integral. And now the new terms that appear are due to the interference term, right, between the, if you want, point particle effects here, and then tidal effects here, plus of course the other cross term. But technically, the computation can be streamlined in a similar fashion, and one retrieves for these tidal corrections to the energy momentum emitted by gravitational waves. One retrieves the result of this paper here by Vernizzi and collaborators. And then, okay, the new calculation that I wanted to show you is instead the calculation of the angular momentum. Again, following very similar lines. The formula in momentum space is eventually essentially the same, but again, we are now focusing on terms that appear from cross terms of point particle contributions times tidal effect contributions plus the reverse order. And okay, this is the result. Now, again, I don't want to go into the details of the functions. Let me just emphasize that the space of function is exactly the same. There is this logarithm of sigma plus 1/2 and this arc cosh divided by sigma squared minus 1. And therefore, one can perform the analytic continuation again in a very similar fashion, which provides, again, let me emphasize, the angular momentum flux for bound orbits in this post-Minkowskian regime still. Now, maybe as a last comment, how do we check the results? Now, here there is sort of a problem, namely that in this analytic continuation that I mentioned, one doesn't really get generic types of bound orbits. One does get bound orbits, but still in the limit in which the angular momentum is very big, right? This post-Minkowskian regime is basically a limit of large angular momentum, and therefore this can be seen to be related to trajectory which have a large eccentricity. So intuitively this can be seen from the fact that if you try to continue a hyperbola and end up eventually with an ellipsis, then to leading order you will go to an ellipsis which is very elongated, right? Which is the one that you get when you close the hyperbola and eventually start getting an ellipsis. So why am I mentioning all this? Because of course it would be tempting to say, okay, take the result you got with generic velocities in the post-Minkowskian regime, do the analytic continuation, and then expand for small velocities to check with some calculation in the post-Newtonian regime, right? Where people, of course, did a lot of calculations for bound systems. And then it should be easy to check if the result has the same limit. But the problem is that most of the post-Newtonian calculations are done for small eccentricities or quasi-circular orbits, which are the most relevant ones for Largo and Virgo types of events. So, okay, in order to perform a cross-check the result, here I illustrate a technique that one can use, which is start indeed from this A mu nu, and since A tilde mu nu, as I mentioned a couple of times, would be a complicated function in this post-Minkowskian regime of generic velocities, it's actually easier to expand for small velocities as soon as possible. So take A mu nu in momentum space, expand for small velocities, and only then take the Fourier transform. Then the expression is simple. It still involves some Bessel functions, but are easier Bessel functions, essentially. And then at that point, one can do the integration, if you want the integration in this formula and in this formula, order by order in the velocity. And basically, Mathematica is able to do it then. And in this way, we find perfect agreement with the limit for small velocities of the full result. And let me emphasize that this is not completely straightforward, because in order to go to the right order of accuracy in this small velocity expansion, one is allowed to retain just the first order for the electric type tidal contributions, but one actually needs to go subleading both in the point particle contributions and in the magnetic type contributions. Again, just in order to get these terms. And the reason is that, as you can see, the electric type contributions are leading compared to the magnetic type, which are instead suppressed by a further power of the velocity squared. And this is somehow expected, right? Because this other type of tidal deformations essentially need the particle to start moving, because before being affected by the gravitational field deforming them. So they are intuitively, this is the reason why they are expected to be further suppressed with the velocity. Okay, so let me maybe just conclude by mentioning an open puzzle, which is to some extent well known in the community, but it can be interesting to maybe advertise before concluding, which is the following. Okay, let me take any of these radiative quantities that I've mentioned so far. Let me just take the radiated energy momentum for simplicity. If one takes the ratio between the momentum or the energy that is radiated by this type of system as we calculated at order g cube, and divides it by the incoming momentum or by the incoming energy, one can see that for large velocities, so if one takes scatterings of particles with higher and higher speeds, which eventually tend to the velocity of light in principle, one can see that this becomes proportional to this quantity here. So theta is the deflection angle, which in the massless case, which even in the high energy regime, one can take to be some fixed small deflection, right? Some, you know, if the impact parameter is very big, as we said, the deflection will be small. So let me say that the deflection angle is small but fixed. But then, as you can see, there is a puzzling feature, because when expressed in this form, the ratio between the radiated, let's say, radiated energy and the incoming energy is not proportional to some power of theta just, but there is also some residual power of the parameter sigma, which we are sending to infinity, right, when we are taking the high energy limit. So as you can see, even if you fix theta to be some small number, in principle, you are allowed to, seems that you are allowed to radiate as much energy as you want, even much more than the energy that the system initially had, which is of course impossible. And in fact, this seemingly puzzling feature is somehow well known especially in the literature about in some older literature here, sometimes referred to as Kovacs and Thorne bound. So it actually means that this Post-Minkowskian expansion that I was describing at the beginning as being, you know, valid for generic velocity, it is not really valid for arbitrary velocities. It should still satisfy this bound. So if you consider a deflection angle theta, the parameter sigma you're allowed to consider is bounded by this value. So with this, maybe let me just go to my summary and outlook slide. So let me just reiterate the main points. In the first part of the talk, I try to present this eikonal exponentiation, which is a technique that allows us to extract the classical limit of a 2-to-2 amplitude, and I essentially illustrated how this can be used in order to extract this eikonal phase and therefore the deflection angle up to order 3 p.m. And then I instead illustrated how this eikonal exponentiation can be enlarged to an operator framework, which also includes in a systematic way the emission of gravitons and therefore gravitational waves in the classical limit. And I've used it to basically rederive some known results already obtained in the recent literature, such as the leading order emitted waveform and the 3 p.m. variations of energy and angular momentum. And then due to the emission of gravitational waves, and then I also checked, which is in principle a new calculation, even if you know, eventually the conclusion that we get is somehow expected. And we also checked the variation of mechanical angular momentum of the two-body system, checking that indeed the sum over the two particles is equal to minus the contribution of the gravitational fields. And then in the last part, I illustrated how this calculation of the emitted angular momentum can be also performed in a simple way using this eikonal framework by including tidal effects in the relevant 2-to-3 amplitude. So maybe, okay, just to mention a couple of possible directions which will be interesting for the future. Okay, of course, learning more about the order G to the fourth, which I didn't talk about today, is also going to be interesting. In fact, there are a large number of recent results that go already in this direction, but which also have some puzzling features, again, in the limit of high energies, which may or may not have to do with this puzzle I was mentioning here, right? And then, of course, a problem which is open for some time, and it will be interesting to pin down the answer for would be the next to leading order waveform. And then, going instead in the direction of this inclusion of additional effects beyond the point particle approximation, it will be very interesting to see how spin effects can be also introduced. Of course, there is already a large body of literature that I'm not citing, and it will be very hard to do justice to in just the conclusion slides, but it would be nicer to understand more, especially in this limit of in this calculation of radiated observables, and then there is this standing sort of energy crisis problem that I advertised, this Coax and Thorne bound. It's in particular nice that for some simple observables one can indeed go beyond this bound, but of course it's not easy to do for all of them. In particular, it's not known how to go beyond this bound for this radiated energy momentum and angular momentum. So yeah, with that, let me thank you for your attention.
Okay, thank you. Are there any questions?
Can I ask? So I have, hi Carlo, I have two questions.
Hi.
Maybe could you please repeat a little bit the story about logs and how exactly you're going to take spin effects into account?
The story about logs, you mean in the elastic case?
Yes.
Yeah. So this has to do with sorry, let me go back to the relevant slide before I start talking. Yeah. So basically, this has to do with this calculation that Sviwern and collaborators did back in 2019. So what they had done was to calculate this deflection angle, right, that was mentioned for the trajectories of the unbound collision. But they had calculated it in the following way. They had started from the amplitude. They had matched it to an ansatz for the effective potential. So that's why basically I was calling it potential terms. You make an ansatz for the effective potential, you calculate the amplitude, but you systematically drop all contributions of the amplitude that are associated to dissipative effects, just because, if you have a Hamiltonian, you want to have a conservative system that you are describing. And from that Hamiltonian that they matched to this amplitude in this way, they then derived a deflection angle. But effectively, this was a deflection angle taking into account only the first two lines of this equation that I'm writing here. And the result was that in the limit of high energies, they were finding something that scales essentially like this theta squared times gm squared over h bar, as I mentioned, times this logarithm of sigma, right? For very large sigma, this basically becomes a logarithm. And somehow this is puzzling because the corresponding result for the massless case, so which is in principle, the big question was whether or not this high energy regime would reduce to the massless case. And the result for the massless case was known since the 90s and is given by this expression, where, as you can see, this is precisely theta squared gs, and there is no log and no trace of this enhancement, none of that. So what's going on? Okay, eventually in this case at 3 p.m. the answer was that, okay, if you include the effect of dissipative of the loss of angular momentum due to the interaction with the gravitational field, so these dissipative effects that are captured by these additional blue terms, then you have this cancellation I was mentioning, right? If you take the high energy limit now, you see that both this line and this line diverge with this log, but the two things cancel out and leave behind precisely the result of Amati-Chavaroni and Veneziano. And this is true both in GR and in an equalized supergravity. So this does this clarify a bit?
Yeah. Thank you. Thank you.
Yeah. Okay. Then the spin effects, of course, as I said, of course, it's very hard to. It's also a huge field on its own that I've not really worked on myself. So it's in particular there are several questions that are open as far as I understand. One big question is already at the level of the elastic amplitude. How does one go about constructing a two loop, even just a one loop amplitude, right, which is universal in the spin, that really captures the limit, the classical limit for the spin, in such a way that you are sure that you are scattering two Kerr black holes, right? this is, as far as I understand, this is still an open problem, right? And then there are, of course, questions as to how one would go about adding to this 2 to 3 amplitude also the spin contributions. And sorry, let me again scroll back to this. Yeah, basically add in the dots here also the terms which carry the information about the spin. The fact that these things are not only point-like objects without spin, but then we have some interaction with the spin. And then once one does that, one could include them in the calculation I did here, for instance, for the emitted energy and for the emitted angular momentum. And in fact, for the emitted energy, this has been done, in fact, in a companion paper to this one, essentially, but not for the angular momentum, for instance. Yeah.
Sorry, Carlo. Anton speaking here. Sorry.
Hi.
I'm just wondering, I think I have a related question on this tidal effect when you have been just describing this, what you call mass and current corrections. I'm just wondering, how do you know, is this all at this level of the post-Minkowskian time that you need to account for? And how do you know, is it constrained? This is probably what you consider for the 2 to 3 amplitude, right?
Yeah, exactly. So in fact, it was very convenient because these contributions had been already calculated in this paper here by, again, Mugakakos, Riva, and Vernizzi. So what they did was to not actually work in the quantum field theory setup, but they consider a sort of word line approach in which you have the particles word lines and then the interaction with the gravitational field via the metric. And you consider additional operators on the word line, which are proportional to essentially Riemann squared with the appropriate contractions. And the 2 independent contractions that people consider and that eventually are related by the love numbers that also in astrophysics one defines, right? Are these 2, exactly as you were saying, current type and mass type operators, if you want. Now, there is a map between the word line and the quantum field theory, or the field theory, if you want, set up. Basically, as far as I understand, it just amounts to replacing the word line with the phi, scalar.
Okay.
But I mean, for our purposes, we are sure that we are doing the same thing because, as I mentioned, eventually this a mu nu is proportional to the waveform. So, we can just calculate the waveform from our approach and from theirs approach, and eventually we are sure that we are landing on the same thing. So there is no ambiguity in translating from one language to the other.
Okay, I see.
Because we match to the same observable.
I have probably a related question. I came across some papers by Plevka and et al. Who use this word line approach and especially for the spinning case.
Right.
They claim that that's the best formalism, and they claim it has some advantages. So could you comment on that? And
yeah, okay. I guess now, to be fair, of course, it depends a bit what one's goals are, right? So I guess considering an approach in which you start with a classical word line and you discuss its coupling with the gravitational field is very, very natural, and probably, I don't know, I might be wrong, but as far as the efficiency eventually of the calculation is concerned, probably it's actually a good idea if one really is only interested in eventually calculating these classical observables that I'm also showing here. Now, I mean, I think that it's interesting also from a theoretical point of view, the fact that, starting from the quantum field theory setup and then taking the classical limit essentially forces you or, guides you to understanding some new properties. I mean, the classical limit of quantum field theory is something that in principle sounds like a very textbook topic, but in practice, it's not very well studied. All this business of the eikonal exponentiation, for instance, it's theoretically very interesting, but maybe to some extent not very standard in the curriculum. So I think, yeah, starting from a theory which is already consistent and then try to take the limit has also its theoretical advantages, I would say. And then, okay, as far as the final calculations are concerned, let me just say that in practice, as up to now, the hardest part of the calculations have been these integrals that I didn't really mention how we calculate them, but I had a slide about that I skipped over. Yeah, basically a one loop there will be this type of integrals, a two loop there will be this type of integrals here, and the integrals are eventually exactly the same in all the methods. The word line quantum field theory, the quantum field theory proper, the word line effective theory, which are slightly different versions of, you know, setting up the starting point of the calculation, eventually boil down to some hard calculation that you have to do. And more or less, they are all the same up to now.
Okay, thank you. They also claim, I think that there was some claim that in the case of spin, they introduced some spin degrees of freedom. To describe spin, they introduce word line degrees of freedom. And then they have some effective supersymmetry, which I'm not sure this makes too much sense, but...
Yeah, they have this supersymmetry in the sky paper, I remember. Unfortunately, I'm not really an expert on the spin side of the story, so I'm not really 100% qualified to say whether or not eventually everything is fine. But as far as I understand from people that work on that, I think eventually also in that case, the results they get are equivalent to the same. Of course, what they do is, I mean, as I was saying also earlier, really doing the calculation at one loop already, but going to all orders in the spin is an open problem, as far as I understand. What they do is to calculate higher multiple moments that are supposed to be captured by spin 2, spin 1, spin 2, and in principle eventually going higher. So this expansion in multiples, as far as I understand it, is equivalent if done in the word line quantum field theory, in the standard field theory up to now.
Sorry, is this, if I'm allowed, I'm just wondering, when you talk at this higher level post-Minkowskian, like 4 p.m., is this the same nature of this KT bound problem, or there is something more to it?
Yeah, so that's the idea. So, I mean, up to now, I'm not really sure if there is a consensus, but to some extent, people are starting to converge on the idea that maybe this 3 p.m. case was somehow lucky. You know, this fact that there is this cancellation and eventually you can just take the massless limit of the massive result and nothing prevents you from doing that. Maybe was a nice feature that only 3 p.m. has. And as you say, maybe these puzzling features that I was just very briefly mentioning in the conclusion slide. I should get better at using links in order to go from slide. Okay. So here I was saying there are these results that show that at 4 p.m. there are these radiation reaction effects, and seems that if you take the high energy limit, the true high energy limit of these things, you still get infinity. And okay, one problem is that as far as I know, there is not really a massless calculation to compare to. In the 3 p.m. case, it was somehow more striking, right? Because we really had the massless calculation that was, it's GS theta squared, and that's it. There is no log, no singularity. In this case, I think the Lappa, so Raphael Port and collaborators did make some checks in the massless case, but I'm not really sure about, exactly what calculation they did. But yeah, as far as we understand up to now, it could well be that at 4 p.m. the result is just confined to be correct below the KT bound. Yeah, that's a possibility.
Okay, I see. Since I'm just wondering, because there are no extra degrees of freedom, it's just deflection angle times this, and this is what the only freedom you can keep.
No, exactly. So exactly, the problem is that the result is not deflection angle times something which sigma disappears, but there is I think there is a log of sigma that is still there. Mm-hmm. So in fact, as far as I'm told, as far as they write in the paper, there are several cancellations of naive power-like divergences of this sigma. Mm-hmm. But then the last one, which is this log of sigma, does not go away. So,
okay, I see. Mm-hmm.
Tempting to speculate that maybe thinking harder about the problem, eventually one manages to find at least one observable, one component, I don't know, something that has a smooth limit beyond the KT bound, but it's not guaranteed, I would say.
Yeah, I see. Right. Okay. Thank you, Carlo.
No problem.
Any further questions? Okay, if no, then thank you for a nice talk.
Thank you for the invitation.
And yeah, thank you everyone for coming. Have a good evening.
Bye-bye.
Bye.